Earth's core is mostly metal, very iron and nickel rich, but its surface layers are made up of mostly lighter, less dense materials called silicates, or at least mostly silicate minerals. But did you know that there is an asteroid in our solar system that is made up of mostly metal, just like Earth's core? And we think it might actually be an old planetary core that got its surface material blown off by impacts, or at least that's one hypothesis. And in today's video, I got to sit down with Dr. David Williams from Arizona State University. I had to wear my merch. As some of you guys know, I spent a little bit of time at ASU because my PhD advisor moved there at the end of my grad school work. But anyway, I got to sit down with Dr. Williams, who is not only a big part of the Psyche mission, but also has done work on a lot of missions. And I'll just pop a list on the screen to save time for a second. He'll talk about a lot of the work he's done in the interview, so I won't go over it now, but he's done a lot of work in planetary science and exploration, and he's got a lot of expertise, especially pertaining to Psyche. So I sat down with him today to talk about all things Psyche, what the mission's science goals are and science objectives are specifically, and why this is such an important mission. So I hope you guys enjoy the conversation, and we'll jump right into it. Hello, and thank you so much for coming on. To start with, can you just provide your name, pronouns, where you work, what you do, just kind of an introduction, brief introduction?
Sure. Yeah. My name is David Williams, pronouns he, him. I'm a research professor in the School of Earth and Space Exploration at Arizona State University. We are the lead, institution running the NASA Psyche mission, which will be a mission to explore asteroid 16 Psyche in the main belt. My research specialty is volcanology and planetary geology and geologic mapping of worlds throughout the solar system. So that's sort of my interest, is sort of in understanding surface features and surface processes. That's going to be my job on the Psyche mission. I'm also the deputy imager lead. So I am a backup to the primary imager lead, Professor Jim Bell, here at ASU, and our imaging cameras are the ones that are going to take all the pictures of the surface of Psyche. I have a lot of experience working on NASA robotic planetary missions during my career. As a student, I worked on the NASA Magellan Venus orbiter, the NASA Galileo Jupiter orbiter, both during the Earth-Moon asteroid flyby phase of the early 90s and the Jupiter orbiter phase studying the Galilean satellites. I worked on the European Mars Express, Europe's first Mars orbiter mission in the early 2000s. I was a participating scientist on the NASA Dawn mission to asteroid number 4, Vesta, and as well as Dwarf Planet Ceres. And all of that has led to me being involved with the NASA Psyche mission.
So before we jump right into the meat of the science behind the Psyche mission and what it's trying to achieve, I asked Dr. Williams just to kind of cover some brief background and context behind the mission. What is it and why are we doing it?
Sure. So Psyche as a mission is a robotic NASA mission of what we call the Discovery class. It's the relatively small size robotic planetary missions, PI led by a scientist and a science team. Dr. Linda Elkins-Tanton here at ASU is the PI of the mission. The goal of the mission is to send a spacecraft into orbit around asteroid 16 Psyche. And I should mention that every asteroid or small body in the solar system has assigned a number in the order in which it was discovered. So 16 Psyche was the 16th asteroid discovered in the main asteroid belt between the orbits of Mars and Jupiter. What makes 16 Psyche of interest is that it is the largest of what we call the M-class asteroids. And in this case, M stands for metallic. We think that 16 Psyche is the exposed iron-nickel core of an asteroid parent body that had most of the crust and mantle knocked off in hit-and-run impact events.
So the reason I invited Dr. Williams to talk with me today about the Psyche mission is because I'm working with the Geological Society of America, or GSA, this year to promote their annual Connects meeting. The GSA Connects 2024 meeting is happening this September in Anaheim, California, and Dr. Williams will be giving a talk there titled NASA Psyche Mission, Exploration of a Metal World. I will put the time and date details up on the screen for you if you are attending GSA and are able to catch it. In any case, in the abstract for this talk, it's mentioned that Psyche is the first mission to orbit an M-type or metallic asteroid. But why is this important? Why is it important that we go explore a big chunk of metal in space?
Well, we want to try and explore all of the different classes of small bodies of asteroids in the solar system. We've sent spacecraft to the S or stony type, to the C or carbonaceous type. Dawn went to visit Vesta, which is V or volcanic type because it had volcanic minerals on the surface. So, it makes sense to send one to a metallic asteroid, including the largest one, which is the most thorough to explore, and that is 16 Psyche.
So we really haven't been to a world like Psyche yet, and exploring something unknown is what NASA does best. However, are we just doing it because we haven't done it? Or is there some practicality and some answers that we might get answered, say, even about Earth, from exploring Psyche? Well, Dr. Williams says,
we think that Psyche, as I said, could represent a planetary core. And it's really difficult to study the Earth's core because it's down deep in the interior and there's all the crust and mantle in the way. So to have a potentially exposed planetary core open in space, it's really logical to send a spacecraft there to try and orbit and then characterize, what is the essence of that object.
I'm curious, how might a protoplanetary core have ended up, well, one, naked as just a metal core and in the asteroid belt?
Well, the asteroid belt is mostly the remnants left over from the formation of the solar system. Planets have grown and accumulated, but you start off with the interstellar dust cloud, and the dust accumulates into pebbles to cobbles to boulders to eventually planetismals, and those planetismals accumulate into planets, and they undergo in differentiation due to their internal heating, and that's how we end up with the 8 planets that we have in our solar system.
So briefly, I just want to summarize what he said right there. Now, I've talked on my channel before about, solar system formation just in very simple terms, from supernova to solar nebula, dust cloud to sun beginning to form to planets beginning to accrete. Why the inner ones are rocky because they're closer to the sun, it's hotter, and all the volatiles go out to the outer solar system where the ice and gas giants form. And as all this is happening and as planets accrete, as he said, there is a process called differentiation, which I think I should just briefly define because we continue to use this term later in the video as well. So differentiation is this process, for example, on Earth, where as it was forming and it was really, really hot and molten, it was undergoing a process where denser materials sank to the core because of gravity and because it was, so molten and hot at the time that the heat allowed for this migration, and lighter materials stayed and made the surface material, things like silicate minerals. Silicate minerals are just minerals that contain silicon and oxygen. If you look at a mineral formula and it has silicon and oxygen at the end of it, it is a silicate mineral, and this makes up like 90% of Earth's crust, and I think lithosphere. I'll put a chart on here, a pie chart, so you can check my math on that. But I think it's around 90%. So most of the surface material on Earth, or the very, very surface of Earth, is very light, non-metallic material. Whereas in Earth's core, because of this differentiation and layer formation on Earth, it's more dense, it's metallic, it's much different material than at the surface. And that is differentiation. And the way that process allows the isolation of different materials by density, specifically, more metal-rich things being denser going to the center. That is the reason that we think that this asteroid, Psyche, might be a planetary core that became exposed somehow, because having an old planet undergo differentiation to isolate that metallic material and make it become very metal-rich would explain the very, very high metal concentrations on Psyche.
But, in the main belt, we've learned that there has been so much impact events, impact cratering due to the strikes of smaller bodies on these objects. And if you did have a differentiated body, you could have the potential of these low angle impacts that strike and knock off a lot of the crust and mantle, leaving the exposed core. Now, some of that crust and mantle will fall back onto the surface, but still you're going to have potentially a very, very exposed body.
So Psyche's surface material could have literally been blown off by impacts, which is one, insane, but two, if this is true, when did this happen?
It's difficult to ascertain that right now, where we're basically working on a lot of theory. What we do know about asteroid 16 Psyche comes from our colleagues in the planetary astronomy community, and they've pointed all manner of telescopes up at that particular asteroid. And we don't think it's necessarily a 100% pure iron core. We do think that at least part of the surface is covered with silicate materials, fall back from the hit and run impacts. There could be dark material from carbonaceous asteroid impacts on it. Perhaps there's water ice and permanently shadowed, craters like we see on the Moon and Mercury. We do know that there are indentations on the surface from prior impact events. We do know that there is some heterogeneity in the surface, but we just don't know what it corresponds to. That's why we need to send a spacecraft to get up there close. As far as when these hit and run impacts occurred, that would have been very early in the history of the solar system, probably within the first, tens to 100 million years after formation.
So it seems like even though Psyche is mostly made of metal, there is some non-metal material like silicates on its surface, but we don't yet know whether those are from impacts over time that brought more silicate material to the surface of Psyche, or whether that material is perhaps from Psyche's original composition, maybe from previous surface layers it had that got blown off and there was fallback like Dr. Williams was talking about. And so he mentions the importance of the Psyche mission for answering some of these questions. So now we're going to jump into the Psyche mission itself and what exact questions it is aiming to answer. So just to introduce how NASA missions typically work, there are typically very specific, or actually I think always, according to Dr. Williams, there are always very specific science objectives that a mission is kind of based around. And everything that goes into the mission, its instruments, its architecture, whether it's flyby, orbiter, or lander, etc., all the stuff that goes into planning the mission, designing the mission, is based on these science objectives. It all traces back to answering major questions about whatever body we're exploring. In the case for Psyche, there are 5 science objectives for this mission, and they all aim to bring us closer to achieving 3 major science goals, which the goals are a little bit more broad in terms of answering questions that pertain not only to the body that we're exploring with the mission, but also to answering questions about our solar system in general. And so the 3 major science goals that the Psyche mission and its objectives help us achieve include, and I'll link the NASA webpage that lists these down below in the description box, but it includes number 1, understanding iron cores, a previously unexplored building block of planet formation. Number 2, to look inside terrestrial planets, including Earth, by directly examining the interior of a differentiated or layered body which otherwise could not be seen. For example, we can't necessarily go look at Earth's core with our eyes because there's tons of rock between us and the core, but Psyche represents an exposed core, potentially. And number 3, explore a new type of world. One made not of rock and ice, which is what we've explored so far, but significant amounts of metal. So what are these science objectives of the Psyche mission that aim to help us achieve these goals? Well, the first one is to determine whether Psyche is a planetary core or unmelted material. So what is the difference between these 2 possibilities, and what is the significance of answering this question?
We think that asteroid 16 Psyche differentiated crust mantle and core would have had a molten iron nickel core. And, that would have solidified in a couple of different ways. It could have solidified from the outside in. It could have solidified from the inside out, the way the Earth's core is in the process of doing. Or it could be just a piece of unmelted metal left over from the solar system. Or it could be a reaccretion of a bunch of metal fragments. Or maybe it was broken apart and they all reaccumulated. So there's possibilities, different scenarios about what this asteroid could be. And so we want to try and figure out which one of those scenarios is likely to explain Psyche's origin. And to do that, you need to have measurements from several different types of instruments. And that includes a magnetometer, So if we get into orbit around 16 Psyche and we discover a homogeneous magnetic field all over the planet, then that would suggest it would have been a molten core that then solidified in the magnetic field. If you fly over and you don't have any magnetic field at all, then that might suggest it's a piece of undifferentiated metal. If you fly over and there's different parts of the surface that have different magnetic domains, that might suggest it might have been fractured pieces of metal that then reaccumulated or redistributed there. A visible imager to image the surface for its morphology and topography, but also look at its mineral composition and for silicates and sulfides are often found with metals. And then a gamma ray and neutron spectrometer, which will give us elemental abundance of major elements on the surface. And then using the high gain antenna, which we use for communication, you can use that as a gravity experiment to understand the density distribution inside the asteroid as you orbit around it. So those are sort of the four main instrument things that are going to provide observations and measurements of the surface.
Dr. Williams mentions trying to obtain some information about the material on Psyche's surface and the distribution of different materials across the surface. But what about ages? Can we do any very specific geochronology on this mission? I've talked on my channel before a lot about isotopic dating and how if we look at the composition of rocks, specifically what kind of isotopes they have in them, we can get a numerical age for that rock, depending on the rock and the isotope system and whether it's been altered, what kind of rock it is, all these things. But anyway, in general, we can use geochronology like this to date rocks on Earth. But can we do this with remote sensing on the Psyche mission?
The instruments on Psyche are not optimized for doing that kind of geochronology. In my mind, you sort of need to do a reconnaissance mission first, an orbiter mission to characterize an object completely because the object is rotating as the spacecraft orbits. You get your global context there. And that's where you identify what is there and where it is on the surface. And then the follow-on mission would be the one where you bring in the next generation of instruments, because then you will know what kind of a measurement you want to make for something like isotopic composition, and you would know where to point it on the either from orbit or send something down to the surface to do that.
Okay, so although this mission will not collect any isotopic data to numerically date the rocks on Psyche, the second objective of the Psyche mission is to determine the relative ages of regions across Psyche's surface. So how are we going to determine these ages if we're not using isotopic methods? Well, the key here is in the term relative. Just because we're not looking to do any numerical dating of the rocks on Psyche doesn't mean we can't determine relative ages of the material across Psyche's surface. Dr. Williams says,
to determine relative age in planetary, and what we traditionally do with flybys, but more effectively with orbiter missions, is we take pictures of the surface and we identify areas of the surface that appear to have been produced by a similar geologic process or processes, and then we count the number of impact craters on the surface, because the older a surface is, the more impact craters are on it. And really old surfaces will have lots of larger craters, and whereas the younger surfaces will have more smaller craters. And of course, if you had a geologic process like a volcanic eruption or a big landslide, that could bury the smaller craters and mark a resurfacing event. By counting the impact craters on those types of planetary surfaces, and you plot them up on a size frequency distribution plot, you can determine the relative ages of the surface. And then when you apply chronology models that have been developed based on our understanding of impact flux in the main asteroid belt, then you can get models that tell you model absolute ages in millions or billions of years. So that's a whole separate part there. And the imager experiment, the camera that I'm working on, will acquire the images of the surface that allow us to determine those relative ages of the different parts of Psyche.
But wait, did he just imply that geological processes large enough to erase craters might be occurring on the surface of this relatively small body? This brings up a question: just how big is Psyche?
Yes, excellent question. The way I usually use to describe it, I usually have a graphic to show it, but Asteroid 16 Psyche, if it were placed on the surface of the Earth, it would cover about the size of the state of Massachusetts, or the distance between Phoenix and Flagstaff if you're in the west part of the United States. So it is a relatively large asteroid. The key question is that I find fascinating is how small an object can you have that still has enough internal heat to allow geologic processes to occur. For example, the asteroid Vesta, the fourth asteroid Vesta, which is the size of Arizona or New Mexico, had enough internal heat from the decay of aluminum-26 to cause differentiation of that object and the production of volcanic features on its surface. So we know at least something, 535 kilometers in diameter can have the heat to have geologic processes. How much smaller can you go and still have that happen? That's something I'm very fascinated with, a really interesting question. And we may get some information about that depending on what the Psyche mission discovers.
Yeah, that's such a great point, and I'm excited to see if anything comes of that. Yeah, so objective 3 for this mission is to determine whether small metal bodies incorporate the same light elements into the metal phase as are expected in Earth's high-pressure core. And yeah, I couldn't formulate a question for this one. So can you just break this down or briefly go over what this means and why we care?
Yeah, so what we know from studying the Earth is the Earth's core is known to have about 10% light elements alloyed with the iron and nickel in its interior. Things like sulfur and oxygen and silicon, perhaps carbon or hydrogen. These were incorporated at high pressures and temperatures during the formation of our planet. So we want to use the gamma ray spectrometer on Psyche to study the amounts of some of these light elements on the surface, in particular nickel, silicon, potassium, and sulfur. That will give us some information about how much of that might have been included in its core. And by inference, that'll give us another planetary object information to think about in terms of the Earth's core.
So again, this objective, I think, is getting back to a comparison with Earth's core. If we can determine that the light elements present on Psyche in composition and abundance are very similar to those in Earth's core, this may give us more context as to where and when Psyche might have formed within the solar system, as well as provide potentially more support for the planetary core hypothesis. The next, or fourth objective, is to determine whether Psyche formed under more oxidizing or reducing conditions than Earth. And I know you guys, my audience, knows a lot about oxidizing, reducing, typically because I talk about it a lot. But in very simplified terms, this just refers to whether there is a lot of oxygen within the asteroid's metal compounds, and that would be the oxidized case scenario, or little to no oxygen, and that would be the reduced case scenario. But how do we measure this?
Planetary cores are thought to have a wide range of oxidation states, right? Between the relatively oxidized state of the planet Mars, where we think its mantle is very rich in iron oxide, all the way to the very highly reduced state of the planet Mercury, where sulfides are likely stable on its surface. So if Psyche was a planetary core, where does it fall in this realm between oxidized and reduced? And the way that we do that is by looking at the nickel content from the gamma ray spectrometer. The reducing conditions are likely required to produce nickel contents below 4 weight percent, whereas bulk nickel contents above 12 weight percent likely indicate highly oxidizing conditions. So pulling more iron into the silicate phase and leaving less into the metallic phase.
And answering this question will help us to determine the conditions of the environment in which Psyche formed. And he goes on to say,
we're also going to be comparing that results for Psyche with the families of iron meteorites that have landed on Earth. And it would be great if we can actually say, well, Psyche's composition matches this one particular family of iron meteorites. Maybe Psyche is the home of that particular family, just like asteroid 4 Vesta is the origin point of the HED, the howardite eucrite diogenite meteorites that are found on Earth. So that's going to be another factor into this whole thing, is how do these measurements of Psyche correlate to the various families of iron meteorites?
So we might actually be able to tell whether some of the meteorites that have hit Earth could have originated from Psyche. That is just mind-blowing to me. Anyway, moving on to the fifth and final objective, and that is my personal favorite as a geologist, to characterize Psyche's topography and geology. This is the objective that Dr. Williams is most heavily involved with. So let's see what he has to say about how they're going to do this and why.
As the spacecraft orbits Psyche at a variety of different orbits, from a higher orbit eventually down to a lower orbit, we're going to be collecting images. We will map the entire surface with grayscale images, which will give us the surface albedo or brightness. We'll also be looking with our color filters, which will tell us about silicate and sulfide minerals that might be in different parts of the surface. But we're also going to be looking at the surface at different look angles. So not just looking down nadir, but looking from different directions. And those images at those different look angles can be processed through a computer to generate topographic models of the surface using stereophotogrammetry or stereophotoclinometry. And that will give us the topography of the surface. So we will know not just what it looks like and how bright it is and information about what its composition is, but we will also know the topography. And when you have those data sets together, we'll be able to construct a geological map of the surface, including a correlation of geologic events to basically create a geologic timescale and chronostratigraphy.
Geologic mapping was also Dr. Williams' main responsibility on the Dawn mission to Asteroid Vesta and Dwarf Planet Ceres, and now it's what he'll be doing for Psyche. But why is it important for us to develop geologic maps for planets, moons, and asteroids? Well, global comprehensive geologic maps provide us a really important baseline for understanding the surface processes going on a particular body, as well as, and especially, its history of geologic activity. On Earth, for example, mapping and studying geological features on Earth's surface is how we understand how it's evolved through time. In other words, how these surface features were formed, how they were eroded, what drives this geologic activity, and how long it's been going on for. And the same goes for other worlds. And with a world as unique as Psyche, this could even answer some of our questions about Earth that we can't find at the surface. But if we think back to the three main science goals NASA has for this mission, understanding iron cores, looking inside terrestrial planets, and exploring this new type of world, one thing is missing from this picture that is certainly highlighted in more mainstream media, and that is mining potential. This asteroid is made mostly of metal, and on Earth, we spend a lot of money mining for metal. So could Psyche be a potential site for space mining in our future? Well, there have been a few very headline-y titles of articles that claim that Psyche's metal content is worth $10 quintillion. So is this a real calculation, or is this a bunch of baloney? And even if it is real or fake, is there any focus on potential for mining in this mission, or is that more of a future thought?
Yeah, it's sort of a fun thought experiment that our PI did. You know, she said, suppose asteroid 16 Psyche, we know its size and mass. Suppose it is mostly iron nickel, and suppose that it has a distribution of iron, nickel, and platinum group elements typical for what we see in iron meteorites and what we know for the Earth's core. And she did this calculation that asteroid 16 Psyche has metals that at current time would be valued at 100,000 times the gross national product of all nations on Earth, which is $10,000 quadrillion. Now, obviously, if you took all of those metals and brought them down to the surface of the Earth, the metals market would crash. Their value would drop precipitously. So, you know, it's not really going to be worth that much. What's really interesting about thinking about it is the concept of space mining, and are any metals or materials on Psyche going to be useful to be mined for a spacefaring civilization? That is something that is a very, very complex thing to do. I mean, whether you use robots or whether you use people on low gravity bodies to try and extract materials, it doesn't need to be Psyche. It can be from near Earth asteroids as well, or, you know, also the surface of the moon. These are all things that need to be studied, because having people work in those low gravity environments in this kind of an industry where you can't use, liquid water as a lubricant to mine, for example. These are all factors that are involved. So we're not really thinking about that on this mission in terms of actual, hardcore science. It's just sort of fun thought experiments to think about. I guarantee you, based on every other mission I've worked on, we will be surprised by something. I don't know what that something will be, but something that we did not expect based on all of our research will present itself in some way. That's sort of the exciting thing about planetary exploration that we all have to look forward to.
So we've talked now about the science of this mission, what science goals and objectives it has. But what about the mission architecture? This refers to what kind of mission it is, and this one is an orbiter. It will go and orbit Psyche. But for bodies like Io and Europa, moons of Jupiter, orbiter missions are exponentially harder and more expensive than flyby missions because of the amount of fuel it takes to keep the spacecraft in orbit around such a small body with such small gravity compared to, say, a planet. So why is the Psyche team choosing an orbiter mission? Is this making the mission much harder or more expensive than a flyby mission would be?
Well, I think part of the factor between, a smaller body like 16 Psyche versus, say, Io is in Jupiter's radiation belt. So the radiation that close to Jupiter is so intense, and orbiter's instruments would be burned out in like 3 months. So, the case, and the Europa Clipper is an example of this, is being multiple flyby, but map your flyby so that you cover different parts of the surface in your 30 to 40 flybys. That's the way you get global coverage without actually being in orbit. So, that's certainly what you need for Europa Clipper and what would be needed for an Io mission. In the case of 16 Psyche, we're out at the far end of the main belt. There's no radiation concern there. It just makes sense, to go, rather than do a flyby and do sort of an initial look or initial reconnaissance, to go straight to an orbiter to get our global characterization of the surface.
So Psyche launched last year in 2023. So it's got to be pretty far along by now, right? Is it at Psyche? Where is Psyche, the spacecraft, now, and how much longer is left?
We launched on Friday, October 13th of 2023. It was a good launch. Yeah, that officially starts what is called Phase E. E is in Edward in NASA parlance there. That is the operations phase. So from launch, you do a 100-day initial checkout, which we did in December and January, December last year, January of this year. And now we are officially what is called cruise phase. So we are cruising through the solar system. We are using our solar electric ion propulsion. We are out in the main belt right now. We're going to go outward, and then we're going to come back in, and we're going to fly by the planet Mars in May of 2026 for a gravity assist momentum boost. And then we will spiral back around and then back out into the solar system to eventually catch up with asteroid 16 Psyche, and that will occur in August of 2029. And then we will be there for about 24 months, orbiting at successively lower orbits, optimizing each of our science instruments to carry out and answer all of those science objectives we just talked about.
So let me reiterate that. 2029, guys. Space exploration is really the long game, especially when we're going so far from Earth. This is why, like I talked about in my webinar with iTelescope, having gas stations on the moon would be really nice and useful. But anyway, I won't get into that now. This talk is about Psyche, and we will now jump to the end of the interview for one final question with Dr. Williams. So just to finish out the interview, if there's a student listening that's interested in getting involved in space exploration or mission design, what would be your advice to them in terms of how to get started?
Well, the easiest way for students is if you go to a university that has a planetary program where the faculty are involved on NASA flight missions. Arizona State, where I'm at, is a good one. So is the University of Arizona. So is the University of Colorado. So is Caltech, Brown University, or Washington University in St. Louis. And there's just a bunch of them around the country. So if you're in a high school and you want to think about that, just start exploring the internet, talk to your high school guidance counselors, ask about planetary science programs, and If you're attending the Geological Society of America meeting that's coming up in a couple of weeks, please stop by the Planetary Geology Division booth. They usually have flyers there that list the schools that are doing planetary programs. The officers and staff who staff that booth during the GSA meeting can give you additional information on places to go and look. In planetary science, it's so interdisciplinary. We need geologists, we need chemists, we need biologists, we need engineers, because doing planetary exploration with missions requires all of this wide diversity of expertise.
So I hope you guys enjoyed learning about this incredible asteroid and mission. And if you want to check out Dr. Williams' work, I will link a lot of his publications down below, as well as everything that I have cited in terms of graphics and figures in this video, as well as links to his research page and NASA's pages on the Psyche mission, so you guys can keep up with the mission and its progress. If you are interested in right now on YouTube learning more about asteroids, specifically how we might go about pulverizing them to protect our planet, I am going to send you over now to GSA, or Geological Society of America's channel, to watch this other interview I did with two amazing scientists that are working on this pulverize it method in terms of planetary defense. So go check that out now. I will link that on the screen somewhere. And with that, guys, thank you so much for watching, and I'll see you in the next one. Bye.